Hi. It seems odd to look at this photo and think of this as a place where the world changed. We've talked about this place before, back in theme 1. This is Sicker Point on the east coast of Scotland, where James Hutton first recognised the importance of unconformities. What I want to do in this lesson is revisit that idea, to think about how unconformities form, and then how we can use those to establish the relative age of rocks and events. Let's remind ourselves, to start with, how unconformities form. So we start out with the deposition of a series of sedimentary rocks. So that happens over a period of time. That finishes, those becomes rock. They become rock, sorry. There's folding, perhaps, there's erosion, subsidence, and then we get the deposition of a second series, a younger series of sedimentary rocks, creating an angular unconformity. That's what shows us there must be a gap in the geological record. Now this is labelled a non-conformity. We could call this a heterolithic unconformity. We have intrusive igneous rock that's formed at depth. It gets weathered, eroded and exposed at the surface. We have more sediments being deposited on top. And we have two rocks then that are together that can't form together. So we have intrusive igneous rocks that must form at depth, sedimentary rocks, unmetamorphosed sedimentary rocks that must form at the surface, found together, therefore there must be a gap of time. We may even see big fragments of the igneous rock that have been eroded away and incorporated into the sediment as well. Both of these indicate there's been a gap, a break in geological time. We can see these features in lots of different places. The Grand Canyon, for example, demonstrates several unconformities. One of the most obvious is shown in the photograph here. We've got an older series of rocks of Precambrian age, very, very old rocks, that have been tilted and eroded. The Cambrian rocks that sit on top of those haven't been tilted, haven't been eroded, so therefore they must have been deposited after that erosion took place. So those older rocks had to have been laid down, cemented together to form a solid rock, tilted and eroded before those younger beds are laid down. So we know that the beds that have been tilted and eroded must be older, the beds that haven't been must be younger. Okay, what I'd like you to do now is have a go at question 9 on pages 14 and 15 of your Theme 9 booklet. You will need to use your geological timescale to help you to answer these questions. Have a go at that now. Okay, let's see what we've come up with. So I gave you a series of 4 photographs of unconformities. The first one is one we've seen before. This is the unconformity at Sicker Point, the one that James Hutton first worked out that geological time must be huge. I asked you to identify the plane of unconformity. Where is the unconformity? There we are. We see it running across the photograph like that. You can see it's where the beds change significantly. And why then did this give evidence for deep geological time? Because there's a massive difference in dip, because there's erosion then of a hard rock, and we also get a change from a deep marine environment to a desert terrestrial environment. And crucially, all of those things take a lot of time. There must be a lot of time for these things to happen, and there must be a big gap in time between the mudstone and greywacke and the conglomerate. Okay, if we look at the second one, I need to apologise again, I'm afraid, for using an old-fashioned term in your booklet. It should be Paleogene rather than Tertiary. For this one, we need to measure the difference in dip between the two. There's our unconformity, which we should have highlighted. And the difference in dip, it's not always particularly easy to measure here, but it's somewhere between 30 and 50 degrees. The missing geological periods, though, are more straightforward. The Triassic, Jurassic and Cretaceous are all completely absent. They're all missing from this exposure, the whole of the Mesozoic era. Something like 200 million years or more missing from the record. If we look at the next one, we can highlight the unconformity quite clearly there. And the Ordovician rocks here, some things that clearly happened to them. They've actually been formed into a symmetrical synform, a downfold. We're going to look at folding in more detail in theme 13. Now, for folding to occur, there must have been an orogeny, and it has to be an orogeny after the Ordovician period, but before the Devonian, because the Devonian rocks haven't been folded. You know, there's a gap in time here. So the orogeny that we see here is the Caledonian. The final unconformity we're looking at, this one, again we've got a very obvious line of unconformity. Quite a few geological periods missing here. So we've got the Carboniferous, Permian and Triassic periods all absent. And we now need an event that's folded those Devonian rocks but hasn't affected the Jurassic rocks. So something that occurred after the Devonian but before the Jurassic. The orogeny that must be is the Variscan. Okay then, to conclude. Unconformities are a really important feature in the geological record. We've seen their importance in terms of telling us about deep time and the fact that multiple cycles of rock forming must occur throughout geological time. But they also allow us to date rocks and to date events. By applying our understanding of how they form, we can actually start to really reconstruct events and their timing from the observations we can make of the rocks. Next time, we need to move on and look at our last two methods of relative dating. I'll see you then.